So for most of this class, we have discussed computer architecture in a pretty abstract way. For example, we've covered topics that may be kind of hard to picture physically, such as SR latches, the flip-flops, and data paths. But now that we understand these in kind of a theoretical sense, we can see how they're put to use. However, before we can dive into how Intel designs microprocessors, we should first review the concept of a central processing unit. Put simply, the CPU processes and executes instructions. Think of it as the brains of a computing device. While it is of great importance, it is not a standalone device in the same way there does not exist a brain without a body to send and receive signals from. The CPU is located on the main circuit board and is logically and physically separate from the other items such as the memory and graphics chip. If we zoom in, we would see the CPU consists of billions and billions of transistors on a chip that make calculations and store information needed to perform a program's instructions. These transistors are basically used to represent a bunch of ones and zeros, and as we have seen from this class, both data and instructions can be represented in this format. Another important concept here to touch on is Moore's law, which is the observation that the number of transistors that can fit in a microchip doubles roughly every 2 years, even though the cost of computers is halved. This means that as time goes on, um, we can get faster computers for cheaper and cheaper every year. Most desktops and laptops have a dedicated CPU, meaning that they have a standalone chip. Some smaller devices, such as mobile phones, have chips that contain a CPU with other peripheral devices attached. This is called a microcontroller and is used when space is more important than processing power. CPUs have three main functions: fetch, decode, and execute. Sometimes the execute step is followed by reading from memory and or writing to memory or registers. Fetching is usually done from the RAM, and the execute step includes functions like add, invert, and or, and so on that are the basics or the basis of more complex functions that we use a computer for. The CPU does not do everything, but it tells all the other devices what to do based on these instructions. CPUs were traditionally single core, but now some feature up to 16 cores. In most cases, modern day CPUs are multi-core. The best way to think about a core is like an engine, so all things held equal, a CPU with more cores has more processing power. This brings us to the concept of multi-threading. Unlike humans, computers are actually pretty good at multitasking, or at pseudo-multitasking at least. Multi-threading is basically where you split a single thread of a CPU into multiple threads that allow a processor to handle simultaneous requests and process multiple instructions at the same time. This tricks the computer into thinking there are more cores than there really are. It is important to note this is not as good as just adding more cores, but it is a way to minimize costs while speeding the CPU up. In recent lectures, we saw how much faster programs can execute if we implement pipelining. Now imagine if we had multiple pipelines. This is the value proposition of multi-threading. Of course, it is important to recognize that code must be optimized by experienced developers for this to work. Another important concept related to the CPU is clock speed. We covered this concept extensively this semester, so there's no need to go into great detail. It is sufficient to think of clock speed as the number of instructions that a CPU can process every second. Furthermore, this metric is only useful when comparing processors in the same family and generation. Overall, the CPU is an extremely important device, regardless of how many peripheral devices it uses or connects to. Now that we've reviewed the concept of a CPU, we can begin to discuss Intel. Intel is the oldest microprocessor company, and their chips are used in pretty much every field you can think of. Their first chip, the Intel 4004, was made in 1971. This chip was 8 bits, which pales in comparison compared to the 32 and 64-bit chips we see today. To appreciate this importance, think of how closely the MIPS architecture is tied to the concept of a 32-bit word. Intel is especially proud of the backwards compatibility that their chips feature. Each chip is built on the previous one to make sure the older versions of their chips do not become outdated. To appreciate this, think of how annoying it is when a company like Apple makes it where standard headphones are no longer compatible with their phones without a special attachment. This also relates to the concept of reusability, which is important in both computer architecture and in concepts like object-oriented programming. Early Intel chips were named with numbers, such as 8086 or 80386. Chips from this era are often referred to as having the x86 architecture. Beginning in 1993, Intel began giving chips more regular names, such as Pentium, Core, and Atom. These should sound familiar from some of our practice problems this semester. As we would expect, these product lines will have different features based on decisions made when developing their architecture. For example, the Pentium processor allows for more efficient audio and video processing with extensions users can add. As outlined in my honors option paper for my networks class, encryption algorithms are very resource heavy. For this reason, Intel architecture has developed to support these algorithms. Other features that are present in these different types of chips include multi-core performance, multi-threading support, power management software, and new semiconductor technology. These upgrades are supported by technology called hardware platforms, which include items such as memory controllers, graphic engines, and network interfaces. If the last one sounds familiar, it's because network interface cards are extremely important when it comes to the data link layer in networks. Now that we understand the history of Intel, we can begin to learn some of the basics about the Intel architecture system. There's some basic similarities that span between every current model of chip, so we can start with these. First, every hardware platform has two basic components, a CPU and a platform controller hub, or PCH. We have extensively discussed the CPU already, so let's move on to the PCH. Introduced in Intel by 2008, the PCH is the successor to the Intel Hub architecture, which relied on two pieces called the North Bridge and the South Bridge. These pieces were essentially used to relay messages between the processor and the motherboard. This new PCH architecture addresses the bottleneck that was present between the processor and the motherboard in the hub architecture and eliminates this by putting all the North Bridge functions in the CPU die and allowing the PCH to support all of the South Bridge functions along with a few old North Bridge functions. In this new architecture, a system clock is infused into the PCH, and the Flexible Display Interface, or FDI, and the Direct Media Interface, DMI, serve as connections between the CPU and the PCH. These two critical components are surrounded by a number of other components that are usually add-ons on the customer side. The first we will look at is Dynamic Random Access Memory, or DRAM. This is a type of RAM that Intel offers that is much cheaper than static random access memory, or SRAM. Typically, this memory is used to store data that a computer needs to execute the current program that is running. Another component that is typically added on the customer side is boot read-only memory, or boot ROM. This is a chip that contains instructions to tell a computer how to start the operating system. Additionally, customers often add non-volatile memory, such as internal or external hard drives. On top of all this, a fair amount of glue logic is often present. Now, this is basically just a logic circuit that is used to connect various other chips and circuits together. So the first example of recent Intel architecture we will look at is the Intel Core i7 system, which is an example of the two chipset architecture, so with CPU and a PCH. This particular system is designed with an Intel Core i7-4779S processor. This 64-bit processor boasts some impressive features, such as 4 standalone CPU cores and 2-way multithreading per core. Because of this, a computer built on this chip will operate like it has 8 standalone 64-bit CPUs. Another feature present in this chip is the integrated L1, L2, and L3 caches. From our class discussions, we know that a cache is a type of RAM that is used to hold information that the computer will need in the immediate future. Because of this, and the whole concept of hierarchy of memory, it takes relatively little time to access the data in this cache. The L1 is the fastest cache and holds the least amount of data, and the L3 is the slowest cache and holds the most amount of data, and is shared between the 4 cores. This chip also has a built-in 2-channel DDR3 DRAM controller. This is outside the scope of this paper, so it's sufficient to know this controller just makes sure that all the caches are coherent. This system also features a DMI, which we covered earlier. Additionally, this chip has an integrated memory controller, or IMC, which can be configured via the basic input-output system, BIOS, and handles input and output to the RAM chips. This system is linked to an external devices using a peripheral component interconnect, PCI and PCH, which we already covered. Specifically, the PCH is used to handle memory, graphics, USB interfaces, Ethernet LAN ports, HD audio, and can be linked to the DMI, as well as a massive number of input, output, and peripheral devices. Some of these devices it could be linked to include high-precision event timers, the BIOS, the system management bus, SM Bus 2.0, and a real-time clock, or RTC. Essentially, this chip is a powerhouse in terms of processing power and boasts an impressive amount of compatible add-ons. Another example of recent Intel architecture is the Intel Atom processor-based system, which is much simpler in comparison. So this is like a microcontroller, so like everything's kind of integrated in place, kind of like a Raspberry Pi. So in this chip, the controllers and peripherals are already integrated, so there's no companion chip like a PCH is needed. This system is built in the Atom processor, which is a 32-bit chip that is often used in embedded systems where size and power consumption are issues. This processor features a DRAM controller, PCIe, E for Express interface, display controllers, real-time clock, and timers. To expand and connect to peripheral devices, the chip uses the PCIe. Simply put, this chip is small, efficient, and highly integrated out of the box. Though by no means is this paper exhaustive, I hope that it serves as a primer for some of the basics of Intel architecture and the various product lines the company offers. Thank you.